when it comes on to seismic, and the information that are given are like the Mach spectral response acceleration of the short period, which is S sub SS subscript is equal to 0.5 G, right? And S1 is equal to zero point 0.2 G. The importance factor E is equal to 1.5, and R, which is the response modification factor, is equal to 8, right? The site class, I hope these are not unfamiliar to you. Site class, right, is D, and the period, for the short period, or this period, is equal to 1 second. Long period is equal to, in this case, 18 seconds. All right, and this is a steel structure. All right, steel structure. Okay. Um, if you are given a question like this, and the question is asked to find the base shear and distribute the load. Anybody, you can just help me here. So the first thing that you're going to find, right, or the first thing you're going to find, let me know if you're seeing my board properly. The first thing that you're going to find, I want to use my, this thing not giving me justice. All right, so let's try again. Let's try it again. Keep moving because of the two screen. Let me see if I do one screen. You see my screen still, right? All right, so the first thing you're going to do, right, which is basically A, all right? So A, you are going to find the seismic coefficient of the maximum considered earthquake response acceleration parameter. And no doubt, so you're going to find site, right? The site coefficient, all right, coefficients, right? And what is referred to as the maximum, are you see my screen? Maximum considered earthquake.
Yes, sir.
Yeah. Nothing is writing? Seriously? Oh my God. You're seeing the screen, but nothing is writing. Let me share it again. Okay. Okay. All right. Let me know if you're seeing it. And you see that writing there? All right.
No, sir, not seeing it
No,
either.
sir. No, sir.
Ooh, this is crazy. All right. Let's get over that. Well, can you see the board behind me?
Yes, sir.
All right. Let me go back to that. Okay. Unshare. All right. Stop share. All right. Let's share again. If not, I'm going to try use a Jamboard. Let me see if it's going to work. All right, let me know if you're seeing now in terms of my writing. You seeing it? Oh, not being shared. All right, all right, all right. Come on. All right. You seeing the screen?
Google Meet, sir.
Oh, okay.
Sir, just share entire screen, sir.
Entire screen. Okay. All right. So let's go again. Entire screen. Entire screen. All right. Share. Come on. This need to. So, still seeing the Google. The Google. Still, I see the Google. Seeing the board. You see, I have S on it. All right. Good. Thanks. All right. So the thing we're gonna do now. All right. So let me just do this quickly. So the what they call it now? The site. So we're gonna look at finding the site, which is the site coefficients, and these are some equation that you would have already will be provided, which is the site coefficient. So this is A, right? So the site coefficient, right? And what is referred to as the maximum considered earthquake response, targeted response, spectral response acceleration. All right. So this is the first thing. So the you will come upon so so the first thing, first equation you have here so is S M S, which is a short for short. All right. Response is FA, right? S S for short, and then you come upon another equation, which is for the 1 second period. SM is equal to, I want you to note V. One is A, one is V. So A there, S1. Okay. All right. If you should, I'm not sure how many of you are. Well, let me see something. Do you have thing there? Oh, how many of you have the code, the ASC7 code with you right now?
Sir, I do.
Yeah. All right. Just pull it up for me. I just want you to go through it quickly. All right. Da, 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 da. So I want you to just go through with it. So everybody just pull it up for me quickly. All right. All right. So when you go to table, these tables will be given. So from table, right? We call now table right, 11.41 dash one, 4 dash one, and 11 dash two. Okay. So when you look into that table, what you're gonna find is you're gonna find what is for FA. So FA here, FA is equal to 14. Are you seeing it? And FV is equal to 2.2. Are you seeing that? Let me know. Are you seeing that? No?
Sorry, I said tables 11-4
Yeah,
point.
11-4. Yes. All right. But nevertheless, that table gives you the information on FA and FV. Just remember that. All right. The so in terms of the calculation, um, then right, S, so we're going to work it out. Replace the SM, S is equal to zero point 0.4 multiplied by, and in this case, we had mentioned that S, so S, S is equal to zero point 0.5 G, and S1 is equal to 2.2. So in this case, the side class for this is D. It's in my in the it's in my board in the back in the back on the black on the board on the board. And the SS is 0 0.5 and the S1 is 2.2. Mm-hmm. So you see the 1.4. So we're using the S now. So the S5, which is SS, which is zero point 0.5, that is equal to, you can just give me quickly if you have the answer, zero point 0.7 G. And SM1 is equal to 2.2 multiplied by, um, wait, this is which one? Something else. Oh, I saw what you were saying, Javarsi. Mm, S1 is what? Zero point 0.2, sorry. So that's supposed to. That what you were saying, Javarsi. So that is point, S1 is zero point 0.2. Yeah, yeah. All right, so this is 0 0.2. Okay. All right. So what we need to do next is all right. So when you multiply that point two, let me just erase that. All right, so erase this. So this is supposed to be point two. Come on, quickly. All right. So this is supposed to be point two, and this is equal to what? This is supposed to equal to point four G. Okay, 0.44 G. Okay. Yeah. So this is supposed to be 0.44 G. Down a little. All right, G. Okay. All right. So so now we have these answers. All right. So we can move on. The next thing you're going to find is the design, what is referred to. So I say this, I call this B. So the design, sorry, the design, right? The design spectral, spectral acceleration. All right, parameters. And I would have said parameters. All right. In finding that, the formula for that is design ST, S is equal to 2/3, right, of SM1, and we know that this would give us 2/3, right, multiplied by, which is this.
Sir,
Say
SDS
the
is two-third of SMS, right? Not
SMS.
SM1.
Sorry. Yeah, this is SMS. Sorry. Yeah. All right. So you're following, man. Good. And that equals to. So I don't have to go through this then. It seems
Go through it, sir.
you all have done this already, and but I'm glad that you guys know. All right. So that is, yes, SDS, which is the design spectral response, the design for the short period. Okay, so come upon that, and then we're gonna have SD1. And SD1 is same thing, 2/3 of SM1, okay, which is equal to which is equal to 2/3 multiplied by 0.44, which is equal to what? 29G. See that? All right. So after you have found that, so BA, then we are going to look at, where is this now? Okay. All right. So the next thing you're going to find is the design. Sometimes just to kind of have an under idea, what is the design, the seismic design category um, for this. So the seismic design category. So C, all right, so, right, fine, which is seismic design category. SDC. In finding SDC, again, if you should look in table 11.11-6-1 and 11-6-2, right? What I have stated earlier was that this building is a hospital. So what is important is the risk factor of this building. Remember that. Okay. So if you should look in the table, um, you know, let me see if we can pull up the table here because I think that kind of help with some of the understanding. 11, 11. All right. So 11-6. Um, just gonna share it in a while. 11-6. All right. Let me see. Let me know if you're seeing my screen. All right. So you see 11-6, right? 11.6-1 and this. So what is important here is the risk of the building. So it's a risk. It's a hospital, right? And the risk vary based on, we know, in terms of the level of occupancy and so on. I would expect like a hotel to be more so a risk. I think it's more risk three, category three, and other like, oh, your homes maybe, because it's not a lot of people in that, maybe a risk one or two based on the occupancy. All right, so you get this, right? You see the table? Are you seeing it? No. Yes. All right, good. All right, so just kind of, so this is a table, and based on the design, um, the design spectral acceleration that we're dealing with, DS. So you have the SDS and SD1. So this is where you go to kind of help regarding the design category that you're dealing with. But in this case, so let's go back to the board. In this case, the design category that we are dealing with here, based on the based on two things, which is the D, we call it now the SDS is equal here to 29.9, yeah, G, and SD1, right, is equal to, what is it equal to now? All right, so if you should look in the table for this figure, right, you recognize that for 29 SD SDS 29, which falls somewhere here. Where is it? Is it 20? I said 29. Is it 29?
The
Sorry.
SDS is 0.47.
Yeah, the SDS, sorry about that, it's 0.47. So SDS 0.47, it falls here, which is D. And the SD1, which is 29, I think I make a mistake there, which falls somewhere, where is it now? 29, which which in terms of the category, yeah, see the category 4, and that would be greater than 29, which is here. No, yeah, greater than that. Okay, yeah, which is this. You see that? All right. So let me just kind of let me erase that. So SDS, SDS, SDS is four is 4.47, and SD one is 0.29 G. All right, so we are clear. So this give you a SD of D. Okay, then you are going to find, so the next thing, which is D. All right.
Sorry, question. Sorry.
Yes, go
How
ahead.
did you get the one for 0.29? I don't
Hmm.
see which one does it match with in the second part of the table.
Here, which part? Where this match?
Like
Which is S?
where does it
Yeah.
fall? Because
All right, I'm gonna
ratios
go
I
to
said
it.
the last one is
So this is where it falls. You see where
it
it
says
gets
less
like,
than
no man. SD1 is greater than this.
oh it's greater than 0. Okay, sorry.
Hmm.
Got you.
Hmm. All right. So yeah. All right. So that. So now what is important now to find is, so after you have found that, you are now going to find the seismic base shear. So the seismic base shear. So find, right, seismic, all right, base shear, and which is V actually. And seismic base shear, we know that the formula is the seismic response coefficient, CS, um, times W. Okay. All right. Let me just go back to the board because I don't think I've put it on it before, or I could just put it here. Let me just put it down here. Let me just put it here. All right. This thing not giving me justice at all. One, two. This not look right at all. All right. This is a building. I don't know what that is actually, but nevertheless, the loading on the building is as follows, right? So on this floor is 918. I think I have 918. I think this is supposed to be keep. Uh, let me just see. Let me see if I can present that better. All right. Yeah, there's a line, It'll take too long. I know there is a line. Say that again. Text. Which which one? This is a ruler. Oh, there's a square there. Where this is? This? Oh, okay. Okay, thank you, Joe. All right, good. All right, so I feel like it'll take forever though. I could use my board, it feels like I'm going back to AutoCAD. On the T. All right. All right. So each floor, so we have starting here. I'm almost asking if there's a copy command. All right, all right. I think we have it like that. Good. So the height of the building. All right. So each floor. Let me see. All right. Where is the? All right. So the weight of the floor. This is the roof level is just say here 840. This is 918, 918, 918, 918. Okay. All right. The building is 55. Let me just tell you the height of the building. All right. It's 55 point dot feet. Okay. All right. So now we want to find the the seismic, the base shear. In finding the base shear, what is important is finding based on the response coefficient, the seismic response coefficient of of C sub S, right? What you want to do is to ensure that so E, right? You want to determine, right, the what is referred to as a period, all right? The period, okay? And the period based on table 12.8-2,
Sir,
okay?
but didn't you give us the period values a while ago? You
All right,
said T
so
was 1.
yeah, there are, what you're going to find is that I've given you the period. I gave you the period. Let me tell you what I gave you. Wait 1 minute there. Um, I believe the period that I've given you, there are two couple of periods. The small period, which is TS, right? TS. Am I right about that? Mm-hmm. Let me see. Let me just a minute here. Mm, yes, I've given you a period, but this period, it is like a, how should I say? It's like it's like a window. Yeah, it's a window. It's a window. Yeah. Let me just confirm something. Let me just confirm something here. Mm. All right, so the TS, TA. All right, I think that T um, is a period in which there should be um, the response, the fundamental vibration of the structure to fall within. But what I can say is that this period will be the period based on the structure. I think that period is based on the ground, the area, the location, all right? Because they are within certain location in which you expect a certain period, especially long period. But what I'm about to do will be of importance, all right? You get that?
Yes, sir. Got you.
Mhm. All right. So based on the structure, all right, based on the structure, can somebody find 12, table 12.3? All right, all right. I kind of want to give you a visual of this somewhat, so you can have an appreciation. So 12.3, 12.3, 12.3, table 12.3 is not there. No. Wait, 1 minute there. 12 point. Oh, sorry, 12.8. Sorry, this thing written so fine. So it's 12.8. So, yeah, 12.8.2. 12.8. Yeah, which is 12.8.2 here in determine the period of the structure. All right. So in determine that, right? This was equation that we come up with, but it's further broken down, which further broken down into a table, which when we did the, let me pull up, did I upload the earthquake formula? But anyway, all right, so this is it. So we're dealing with a steel structure and a concrete structure, depends on what you structure you're dealing with. All right. So this is a table that we use. All right, so based on that, we are going to input these information here, which is, so let's go. All right, so you have an understanding there. So the period. All right, so in this case, we are using, so T A is equal to, which is for steel, um, 0 to 8, right? HN, which is the height of the structure. And this was the equation coming from raised to the power of 0.8. All right, so this gives us, right? Um, gives us, you can multiply 0.696 seconds. Okay, so that is a fundamental period of the structure itself. All right, so that's E.
Sir, wait, what is 0.02? What is that, sir?
All right, let me go back to it. So from this table, to deal with the fundamental period of a structure, of a steel structure, which is a moment structure here, right here.
Oh, sir, I see it. 0.028. Okay, sir.
Yeah. All right, good. So this was a formula that it's plugged into. I think it's further defined. What will be given? All right. So that becomes that. All right. So after you have gotten that, right, as a fundamental period, what you want to determine now is what I refer to as well, this is the seismic response coefficient. So the seismic, so which is, so this is F. So you want to know, determine, right? So you want to determine, right, the the seismic, okay, response. The good thing, these is just a matter of using the table that is important here, coefficients. Um, all right, it's just a matter of what is important in terms of how you approach the table. The response, which is CS sub S, is equal to SDS, right, over R divided by IE divided by that. Okay? We already know SD, right? We already know the design spectral acceleration parameter, which is 0.47, okay, divided by the importance factor that we had importance factor is 1. So 8 divided by 1, sorry, 1.5. All right, let me just kind of give some information here. I think it's on the board. You can see my board, right? The whiteboard. Yeah, I'm gonna put it there. One minute there, please. HN, this part, the HN, the height of the structure. Yeah, 55. Mhm. All right. All right. All right. So we can move ahead. We can move ahead. All right. So we determine this to equal to. So what we're going to do is to find the series of in there of CS. All right. So this is equal to. I think this is equal to. Sorry. Yeah. So this is equal to, anybody find it already? Anybody divide that? Anyone divide that already?
So I got 0.088.
Okay, good. Yeah. So 0.088. Okay. All right. So that is that. Then I'll just shift over now. All right. Just a minute here. All right. All right. Can I just move this, shift this across? Or should I? All right. I could do it like that. All right. Let me do it like that. All right.
Sir,
Mm-hmm.
where do you get your R value?
R value. I've given the R value.
You given the R value before?
Yeah. Mm-hmm. See it here.
Okay. All right.
Mm-hmm.
Sir, look back
Mm-hmm.
at E, determine the period.
Yeah.
Where was the HE, sir? The HU.
H Sorry, it's HN. My bad. What is this HN?
Yes, sir.
Is the height of the structure. So if you put 55 here, to raise to the point 8, then you should get this. Multiply by point. You get it?
Yes,
You got
sir.
it, right? Okay, good. All right. So let's move on in terms of that. So, all right. So we're here. All right. So there are a number of the, what should I say now? The response and the seismic response coefficient that you are determining. And I think you use the, I believe is a smaller, or the smallest of it. All right, so let us continue and I will just conclude that part, show you. All right, so after we have found this CS, there's another CS with regards to the period, based on the period of the structure itself, which is CS, and this is equal to, based on, so this was on the short period, this is now based on the long period, right? And there's a T here, which is R over important factor, which is I. All right. And this is equal to, let me see if I get it right. So we already know that SD1 is 0.29, right? Divided by 8, 1.5, multiplied by what was T? T is, I just put the T here, zero point 0.6 based on what we found there, 96. Okay, S. All right. Mm-hmm. All right. Mm-hmm. All right. So after you have found that, then based on the tables, right? Based on the table, this answer should give you, this supposed to give you, come on, this supposed to equal to 0.0781, and which is t is less than or equal to the long t. So this is a formula that you would use. All right. So
So I'm kind of confused with the T's because
Sir, could you just put TA? Put the
all
yeah,
right.
because you have
Yes,
plus
yes, yes.
signs there.
All right, my bad, my bad. Yeah, I agree with that. So TA, which is a fundamental T of the structure itself. All right. So we have gotten that. Yeah, or the whatever the fundamental T is, because this equation applies to when T or the TA is less than the TL. This equation, and using it with the design spectral response parameter of a 1 second period. If you recognize the two different equation, the two different equation. All right, you get that?
So, sir, basically, for in order to use that CS equation, you have to determine that TA is less than TL, and you gave us
Ye-
TL, and we determine TA.
Yeah. So we
Which
basically
makes it valid.
say that again.
So basically, we calculated TA, and you gave us TL.
Mm-hmm.
TA is 0.696, which is less than, I think it's 1.85 you have for TL over there,
Mm-hmm.
or
No,
something like that.
TL is a long period is L, which is 8.
8. Sir, so
Mm-hmm.
basically that value TA is less than TL, so we can
Yeah.
go ahead
Fuse
and use that.
So what we're doing, we are calculating these different um, CS based on the period, and then we are going to be selecting I think the smallest of the value. All right. So, so we are working out the period, and then we're going to select the smallest period or the smallest CS based on the period. Okay. So right here we have this based on the short period. This is based on the 1 second period. So we got this. But it's just that in order to use this equation, right, it basically giving us an idea in terms of the TA less than. So it's just telling you it's less than the TL. And you will find out as we go along further, where there's a minimum value. Yes, yes, yes. And see, say that over here.
It's on the board in Sarah's background.
Hmm. Hmm. Yeah, in the background. All right. So these are equations that will be given in terms of and the application. Okay. All right. So let's move on. There's another application in terms of um, CL, right? Is in this case, it is it is DS, I mean SD1 multiplied by the long period, right? Squared to this power t to the to the power of 2 r, and these are equations that were given, okay, in finding the seismic response coefficient, and this is equal to 0.29 multiplied by, and t in this case I could call it ta, all right, is multiplied by zero point 0.7 0.696, okay, to the 2 is to the power, and this is 8 divided by 1.5, and this is equal to 0.89. All right. So how should I say now? How do I state this? So each, let me see if I can find this form, this thing there. The so this is the in finding the CS, which is using the equivalent lateral force procedure, right? So basically, we're trying to find
But
these.
sir, the one that you just told us to use, isn't that you? They said that in 12.8-4, it says that's used when T is greater than TL. But
The
we
one I just
already,
do.
yeah, the one with the TA squared.
Hmm. So that is why we are going to rule that out.
There is another one, I think that's a minimum, where they say
Yes. So we're gonna, so
0.04.
yes, good. So we're gonna get to the minimum now. All right. So the minimum. So in this case, so this is used when t, yeah, when t is greater than TL, right? So in essence, I could stop here, but let us check the minimum. Let's check the minimum. So the minimum here, which is CS, is equal to CVE4044 SDS important factor, which is equal to um, and this must be greater than, sorry, it must be greater than or equal to 0.001. Okay, it must be greater. So the answer, when you get this, when you put this in, when we multiply all this, sorry, when you multiply this, we get uh, what is this called? This, okay, an important factor, sorry. zero point 0.5 is equal to 0.30312, and this is greater than, okay, yeah, this about one of that. So it's just a matter of condition in applying these equation. But we can actually stop. Well, you could actually use a t that is less than the long t, right? The equation, and stop there. Yeah, and stop there. So in essence, so now we can find the base here, which is v is equal to, which is this point multiplied by 4,512 kips, which is equal to 3. All right, so that is the base here. You get that? All clear?
Sir, just one clarification. I think you said that we would have used the smallest out of the ones that we use. So in any essence, if we had used the one where we got 0.0310, would it be fine?
No, sorry, I said the smallest. No, this the smallest out, the smaller of this and this.
Oh,
This is a check to say that it doesn't fall. It must not be less than.
okay.
Yeah. So this is a check to say, is this here less than this? No. So therefore we use this. Okay. You get me? All right. What this does, this equation here is to, sorry, undo. What this equation, the importance of this equation is to do a check to ensure that the values that you have calculated above doesn't fall below this figure. Yeah. Conservatively, sometimes I would advise you to. Sometimes we use 0.10% actual. I mean 1%, which is this actually. But this is very conservative. So rather than calculating all of the CS and so forth, we actually use 0.01, and that is it's very conservative. You get that? All right.
Yes.
All right. So the next thing now is to look at what now? All right. Is to now distribute this shear force in each story. You get what I'm saying? So we want to ensure that we distribute the loading in this story. Let me go over here. Um, so we want to distribute this load now. So based on the base shear, so the base shear is right here. Um, so the base shear but we want to now distribute the base shear over the structure. Do you understand how I get the weight? All clear on that? Yeah. All right. All right. So let us go to the um the vertical distribution of this base shear over the structure. So in order to distribute the base shear over this structure, uh, sorry. All right. So we are doing now, and this is all right. I just call it as is the the distribution. So the vertical, um, sorry. So the why is this? Okay, let's undo that. All right. All right. So we're looking at the so the vertical, all right, distribution, all right, of seismic forces. All right. All right. So what we do in order to distribute this, right? There is another formula that will be, you know, given. And let me just check it here. If it is here, all right. This is a vertical distribution formula. All right. So let us apply it now. All right. In order to apply that, which is the what do you call it now? The story shear force. All right, which is denoted by Fx in each story, is C. I think this is Vx. Um, this is what V. All right, V, and that gives you need to find what is the I think this is called the I won't tell you. This is called the vertical distribution factor. In order to find the vertical distribution factor, we apply, there's this formula that is given. All right. So the formula that is given is, oh, come on. All right. So Vx is equal to the weight on each floor, right? Multiply by the height, right? Raised to a factor called um, K, right? How did I get K again? Let me see. All right, K. Let me just go back here. Let me just see something here.
Sir,
Let
the
me show you
code
some.
says for t equals 1, k is 0.75 plus zero point 0.5 t.
Hmm. Which is this. All right. Thanks. All right. For a structure period of zero point 0.5 or less. All right. Um, there's a way. 1 minute. I wonder if I had to work. I have it. I'm not sure if I just a minute. What was the period? All right. So the period that we had gotten was 0.696. When you interpolate between um I think what's the interpolation is between uh, was it between point 0.5, I see a point 0.5 and 2, you come up with a K value. You come up with a K value of the K value that you come up with is, let me just finish the formula here. So it is a summation, right? Moving from, one floor right up to the end of the floor as we sum each the width over the height. Okay. K. So K here is equal to 0.10. All right, based on the period. Um, so what we're going to be doing here now is, this is better presented in a table format. All right, and this is us actually distributing the load over the structure. Okay. All right, so we're going to represent each. So this, okay, we're going to represent it in a table form. I hope that will be the table. All right, so let's go. All right, so here we're looking at levels. All right, and the levels mean in terms of denoted by X. And this, the first level that we're looking at is the roof level, which is a 6. All right, so we could call it 6, 5. And I mean, you could, I could start it at, I guess the Americans, I could start it at 5. So let's go. Sorry about that. So let's start it at 5, which is the roof level. 4, 3, 2, 1. All right. So each of these now, um, here we want to, in terms of the height of the structure, which is denoted by hx. All right, and this is in the unit, which is in feet. All right, so the height of the fifth is 55.5. Then it comes down by, I think each story is about 10 feet high. Um, all right, so this is us defining the stories. I don't think I define it. Um, what is this now? Sorry. So this is 35. So you're going down by 10. Um, and this is 25. And this is 15 from ground level. Here is, so we're actually defining each of these. X raised to K. All right. And we already know what is K. This is supposed to give you 82, right? 0.8. This is supposed to give you 66.6. This is supposed to give you, you can help me, you can just do a double check. 50, I think it's supposed to be 50.73. This is supposed to give you um 35.25, and this is supposed to give you something like, I think, 20.39. All right. The loading on the loading, which is W denoted by WX, sorry, WX. Um, so WX, right? And this is actually in the unit, which is kips. All right. So the load in here is 840, 918, 918, 918, 918. All right. Then we have here the multiple of this. So we're basically carrying out the top, the numerator exercise here, which is this becomes, right, W x, right, h x raised to k, and that is just multiplying that. I think I should move this over a little. All right, I'll leave that open. So this now becomes 69 661.2. This now becomes 61,184. That this becomes 46 1. Um, this becomes, let's see, 1, 2, 3, 4. 1, 2, 3, 4. All right. Okay, this is supposed to be 32,359.5. This is 18,718. Okay. All right. You can actually go ahead and sum this. This now becomes 200 and 228,000. I think 493.54. This here, we already gotten this already, which is 4512. All right, here, which is this is the value of what is called the CVX, which is equal to point 0.3, all right, 0.5. This here becomes 0.2678. This becomes 0.20H. This becomes 0.146. This becomes 0.8.19. All right, this is supposed to come back to 1. All right. This now is where you would now apply the fx equation here to know what is the vertical distributed load, which is which is which this now is fx, and we know what fx is equal to, which is cv, um, right, x, and this is now equal to 17319427. This becomes 71.7. That this becomes 49.84. This becomes 28.83. When you add back all of this, you're supposed to get back your base share, which is that 2. All right. So the formula for the CVX, let me just kind of define it here. This, right, is this, which is this divided by the summation of that. You get it? Yeah, so each of these, so each line you go into, you divide it by the summation of what the loading is on first. So there's a so on the first floor, second floor divided by the total load. So basically, we're applying this the formula here. Because the formula says the summation. Formula is not right properly. So it's a summation. Okay? You see that? Divided by each story. Clear? Is multiply this, multiply by that. Mhm. No. Is it? Fx. This? Where's V? V. We are sorry. We already gotten V already. Yeah. 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 Am I right? Wait, let me just make sure I'm right. So we already have gotten this. What is V? We know V was two,
Yes.
352. You
Sir,
ever see that? Yes.
um, backtracking. I'm following so far here, so backtracking.
Good.
Um, in finding the K value,
K
is it,
value.
is it
All
that
right.
the
So the
period that we using was the 0.696
yes.
microplanet?
So that is a period because it says here. Um, so it is less than. I think it should be less than or equal to. All right. So it says here for structure that have a period, right, of zero point 0.5 or less, K is equal to 1. But our period was
Sir, I
point.
think we use a third one between zero point 0.5 and 2.5 seconds.
Yeah. Sorry. Yeah.
Yes, sir.
Yeah. Yeah. Yes. Sorry. Yeah.
I know we use that one now in purple, but I was wondering if the period that we used to find
Yeah.
this
Is a point. Yeah. Is a 6.6. Point
was
six nine
696.
six. Yeah. All right. So we are good to go. So it won't get more complicated than this. No.
Sir, so like when you're giving us a question, what is the overstrength factor and the deflection amplification factor for? We don't
For
use.
this, we not at this level. It was given, but not for this. This is when you're applying. We call it now. If you were going to factor, if you were going to be doing some factored load and so on.
Okay, sir, because they
But
were given in the assignments. I was wondering.
okay, not I won't be giving you for this.
Okay.
Yeah. All right. Because I mean that will become a little bit more complicated. All right. All right. The next thing that we go on, I think we need to go on the win, right? Win. Let me see the win. All right. So we're all clear. All right. So let's move on. Um. What's happening here? You know, why not giving me that? All right. So let's do a win question and yeah. Mm-hmm. One again. Okay. The third level, which is this. Oh, sorry. All right, let me know if you're seeing. All right, so the third level, which is this here, 44, oh, 44, 46,000 point, yeah, yeah, 46. Let me make sure. How much you got? When you multiply it, you can multiply it. Okay, yeah. Quantity, so it is, so 46,000. I mean, 46. Yeah, 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 yeah. That's what I have. Yeah, you're right. I'm not sure why I didn't. Yeah, that's what I have. All right, some of this. Yeah, 228. 228. All right, let me correct this. All right, let me just correct this. So this is supposed to be. All right, so this is supposed to be. All right, so this is supposed to be 0.14. Yeah. All right. But what I want you to do, just go back through it and just kind of have a fair enough understanding. But I think this is pretty straightforward. All right, good. All right, so that's it for that. Okay, okay. All right, so let's look at a win question. Um, a win question could could possibly need to look at. All right, all right. So the win information. So you could have gotten a structure, somewhat. Yeah, you like it on the computer. All right, all right. All right, let me go to the computer. Um, yeah, I think it kind of better in terms of visibility too. Yeah. All right, I want to, let me just switch over something here. Disconnect that here. Just give me a minute. Let me just take out these earbuds. Got these things. All right, are you hear me? You hear me, right? All right, good. I just want. All right. All right. So we're looking at the win approach. All right. So the win approach, the win question is win question. Come on. All right. Just give me a chance to pull up something here regarding the win information. Cancel.